Good afternoon again. My name is Jirka Hlinka. I'm from Institute of Physics in Prague, and I will be chairing this session. And it's my great pleasure to call the first speaker, which is Dr. Cazorla, from University Australia, and he's going to talk about multiple structural transitions driven by spin-phonon couplings and multiferroic bismuth cobaltate. And I think it's invited talk, so yeah, 30 minutes.
Thank you. So thanks to the organizers for having invited me to talk about this talk I've been done recently, along with my collaborator Jorge Iñiguez, working in the Luxembourg Institute of Science and Technology. So here are my funding sources, which also I'd like to acknowledge. So as any of you should know, multiferroics are materials in which two or more ferroic orders coexist. Normally these are ferromagnetism and ferroelectricity, and which remain coupled to some extent. Right? So one very typical example of multiferroic material is bismuth ferrite. So this material, the ground state is a rhombohedral R3C phase, in which we find out that the electrical polarization is orientated along the 1-1 direction. And we have some out-of-phase oxygen rotahedral rotations along the 3 pseudocubic axes, right? So the magnetic order, in this case, is antiferromagnetic order G, which basically means that the atomic magnetic moments are orientated antiparallel in any directions, both in plane or out of plane, right? So we more or less know this. So there is in bismuth ferrite, there is a competition between this ferroelectric and magnetic phase and an orthorhombic non-polar phase, PBNMN. So when you heat it up, bismuth ferrite at ambient pressure conditions, so at some point it becomes paraelectric and adopts this phase, or if you just keep a constant temperature and you just compress it under pressure, also at some point it stabilizes on this non-polar phase, right? So the magnetic order in this case is also antiferromagnetic order G, which is the same that we found in the ground state. And we find a bit different pattern of oxygen octahedral rotations, right? So multiferroic materials, in addition to this possible coupling between magnetism and ferroelectric, also possess some other very unique properties, like can be electronic and structural properties. So in particular, they are materials which can react quite a lot to external stimuli, and because of that, they are quite promising for different kind of applications, ranging from photovoltaic to information storage and energy storage and conversion too, right? So because of this reactivity to external fields, magnetics or electric or even stress fields, these materials are also called multifunctional, right? And behind this multifunctionality, most of the time we find phase transitions, right? So you apply an external field and the system just changes from one phase to another, right? So I'm very much interested in multiferroics and in phase transitions in multiferroics, right? So because of that, a few years ago with Jorge Iñiguez, we started wondering how important spin-phonon coupling effects could be in multiferroic compounds, in particular in multiferroic phase transitions. So what is this spin-phonon coupling means? So as a matter of fact, when you consider different magnetic order in bismuth ferrite, your phonon vibrations change, right? So this is a calculation based on DFT in which we calculated the phonon frequencies by constraining the magnetic moment to the ground state, which is antiferromagnetic order G, or adopting the ferromagnetic state in which all the magnetic moments are parallel, right? So by doing that, you can then identify one by one eigenvectors in the two states, and then calculate this omega shift, right? That gives you an idea of how important spin-phonon couplings can be. So, as you can see, the spin phonon couplings, how the phonon frequencies are changed when you consider different magnetic order is quite large, right? So we were thinking, okay, so if this is big, so this is calculated in the ground state R3C rhombohedral phase. So how affect these effects to the phase transitions in bismuth ferrite, right? So for that, we developed an extension of the quasi-harmonic approximation based on first principles calculations, about which I will talk about in more detail later, right? In order to get into account the effects of magnetic disorder on the phonon frequencies. In other words, so we know that when you heat it up, a magnetic material, you know, the magnetic moments start to fluctuate, and that has an effect on the vibrational properties, right? So we wanted to take into consideration that particular temperature-induced magnetic disorder on the vibrational frequencies of the material. So we did that, and we did, so this is what is called here unfrozen spins, right? And at the same time, we just did quite a standard quasi-harmonic approximations in which we just constrained the magnetic moment of the atoms to the one that you see in the ground state, right? So for our surprise, we found out that in reality, it didn't matter too much, at least for the rhombohedral, so the polar to paraelectric phase transition, right, at normal ambient pressure conditions. So when you start heating it up, you know, at a temperature around 900 kelvins, you get the paraelectric phase. And we found out that actually the spin phonon couplings didn't have any effect really on that transition, right? So we were a bit disappointed, but then we start thinking, we start analyzing a bit in more detail, and we realized that in fact, if you don't look at the phase transition, you just look at the effect of the spin phonon couplings on each of the free energies to the results. So by using this approach based on DFT, which allow us to take into consideration the effects of magnetic disorder as induced by temperature on the phonon frequencies, we came up with this phase diagram here, right? So basically, these crosses and points are experiential data, and these lines are our predictions. So we found out that if you consider zero pressure, this is pressure and this is temperature. Yeah? So if at zero pressure, you know, with our approach, we could very much, well, quite accurately, predict the phase transitions at the points where experiments get it, right? So one important thing is that if you don't consider this approach in which you have into account the effects of spin disorder, then you never get right these transitions as got in the experiments, right? So in principle, you get some transition temperature that is just unphysically high. Also, on the zero temperature but under pressure, we get kind of good agreement with experiments. And then we found out a very exotic region in our phase diagram that involves a double reentrant phase. So this is this phase here, this region here, in which I put this is in yellow. So if we start from some point around 2.5, for instance, and we start heating up the system, so we start from some tetragonal polar phase with antiferrometric order, we then stabilize an orthorhombic non-polar phase, which is still antiferromagnetic, but after heating it up further, we got, again, a tetragonal polar phase, but in this case now, paramagnetic, right? If we further heat up the system, at some point, we get the paraelectric paramagnetic phase, right? So this is, I have to say that this hasn't really been seen in experiments, but we think because, you know, on the few works that has been done in this material, they have basically focused on finding the phase transitions and the high temperature range, right? But they haven't really looked into these details. In any case, we hope that these results may motivate experimental searches for these kind of effects that we are presenting here. So the thing of having the calculation of Gibbs free energy is something that is really nice because you can, you know, put the contributions to your free energy in separate parts and just look which terms are the really important, which are behind those phase transitions. And that's what we did. So first of all, we realized that anytime the tetragonal or the orthorhombic phase became paramagnetic, its Gibbs free energy it suffered a change of slope so that it became more energetically more favorable, right? So we look into the Helmholtz free energy and enthalpy contributions to the Gibbs free energy, and we realize that the real effect, so the term in which there was the bigger effect, or was the responsible for these changes in the slope, was on the enthalpy contribution, right? And the reason for that is because anytime the system became paramagnetic, the volume of the system expanded, right? So that what it makes is that the enthalpy, which has a pressure per volume term, it gets worse, right? And in the special case of the non-polar phase, this is very extreme. So the system just gets higher and higher in volume, right? So, sorry, this was just for the particular case of fixing the temperature to 2.5. So in this region of the phase diagram that we find out this peculiar reentrant phase. But we did the same for all the ranges that we study. And again, this is the Helmholtz free energy difference between the orthorhombic and the tetragonal phases. So if these terms behave quite monotonously, the enthalpy contribution through this volume expansion when the system became paramagnetic in either of the two phases, it's the one that makes this, is the final responsible for this series of phase transitions. So of course, this phase diagram that we propose from our calculations is very interesting because you have quite successive multiferroic phase transitions. So we start wondering how could we bring back, so this happens at high pressure, but of course for practical purposes we would like to have this at ambient pressure, right? So we start looking by two different possibilities. One was solid solutions, so by making doping, right? So essentially we start doing some DFT calculations, monitoring the enthalpy energy difference at zero pressure, right, between the P4MM and PNM phase, when we substituted in the A and B positions, right, by similar elements. In particular, in the A position, we consider yttrium and also lanthanum, and in the B position, we consider manganese and iron, right? So we found out two possible solid solutions which may present, in principle, that intriguing series of phase transitions at ambient pressure. And one of those is bismuth lanthanum cobaltite and bismuth cobaltite ferrite, right? So this is at 50.5, and this is just with a small amount of lanthanum. Another thing that we've seen also is, okay, so can we tune the energy difference between the polar and non-polar phase by means of epitaxial strain? This is work in preparation, but our answer is yes. So essentially, so here is the P4MM, and this is the PNMA. So when you go down to tensile strains, that energy difference can be really tuned, right? So you see, even at some point, of course, the supertetragonal phase is not energetically favorable anymore, even at zero temperature, right? The thing is that when you have, in thin phase, we have found out that also another phase comes into play, which is a monoclinic phase. So, well, basically there are two, but let's just say is one, which have these properties, right, which have some polarization that is not out of plane or in plane, so it has some direction, right? And it has also this pattern of oxygen tetrahedrals. In this case, however, the CA radius is quite close to 1. So here are evolution of the polarization in plane and out of plane, and also of the oxygen tetrahedral. As you can see, the polarizations on the monoclinic PC phases and the PO4MM, it's quite large, right? So we did exactly the same as we did in the bulk case. So now we calculated the Gibbs free energy for the different phases, the 3 different polymorphs that appears at 0 temperature, and see how as you increase temperature and the magnetic moment and everything changes, how the Gibbs free energy balance was changed. And we have come up actually with this phase diagram, which also seems to be very interesting. So in particular, we have this section here in which we can go from some polar to non-polar to again polar, and even in this region here, even we also see some kind of reentrant behavior, right? So we can actually stabilize a polar phase by effect of increasing temperature, which is quite non-common. So again, if you don't take into consideration spin phonon couplings, you get a completely different phase diagram. So just the last few slides. So this region here is especially attractive for functional properties, basically because you stay in here, so this is kind of room temperature. You can, with an electric field, you can think of stabilizing a P4MM paramagnetic phase or a PCE, so this monoclinic phase, G phase, right? And actually, so you can go from a phase to a high entropy phase or to a low entropy phase by applying an electric field with a particular orientation. So this presents quite high promising prospects for instance, for cooling applications in which, based on the electrocaloric effect, so basically you can go from a phase to another phase which involve a quite large change in entropy by applying an electric field. And because we actually have access to the free energy, we could really calculate that. So what we found out is that assuming that that the P4MM can be stabilized by applying an electric field out of plane, we came up with a kind of reasonable electric fields, not too big. So this is a critical electric field from going from here to here, kind of first order transition phase. And the impressive result as well is that the magnitude of the adiabatic temperature changes are very large, right? So with here fields of 200, you can get changes of 20 Kelvin at room temperature. And in this case, because you go from a low entropy to a high entropy phase, the change is inverse, sorry. So you really are cooling down in moving from one to the other. However, now if you apply an electric field in a way that you stabilize the monoclinic PC phase, which has a lower entropy, you get some kind of like similar effect in terms of magnitude, but now it's not indirect. Now it's direct because basically the entropy decreases so that the change of temperature increases, right? So basically this has like quite promising prospects for electrocaloric effects by applying electric fields and changing the orientation of it. So conclusions. So we believe we have shown that in multiferroic materials, when the competitive phases present quite different structural and magnetic properties, then spin phonon couplings may be crucial in order to predict the phase transitions occurring in them. So as a result of the effect of these spin phonon couplings, we can find very impressive functional phenomena, like for instance, this temperature-driven reactant behavior and giant electrocaloric effects. And we believe that bismuth cobaltite is a good candidate in which to realize all these effects, well by doing solid solutions with iron or lanthanum, or well by growing up thin films. So thanks a lot for your help.
The invited talk, very nice results. So I think the speaker deserves a short question, at least. Yeah, go ahead. Microphone, please.
Hello, thank you for the talk. Sort of as an added level of complexity, did you consider the possibility of spin state transitions?
Of what, sorry? Of
spin state transitions?
Spin?
Spin state transitions, high spin, low spin, intermediate spin.
Oh, yeah. Yeah, so on all these different, antiferromagnetic orders, of course, you may have at the same time intermediate, high spin or low spin, and we did actually work on that quite a lot. So in the particular case of, Yeah, so we check out all that possibilities, and we actually discuss it quite a lot in our last paper in the supplementary information. So it's a bit controversial in bismuth cobaltite, so whether it's a high, intermediate, or low spin. So we deal with all that, yeah.
All right, thanks.
I have a question about your phase diagram. When you construct a phase diagram, I see you only have single phase regions. Have you ever considered this possibility that you may have coexisting phase regions?
Oh, okay. So in our, of course, in reality, I guess you may have, because also this is phase out of transition. So of course you may have coexistence. In our calculations, we have to say, of course, we are considering single crystals and very smooth things. So in reality, probably yeah, that boundaries are not that clear, right? So in our simulations, so answering to your question, we haven't considered coexistence between phases, but of course that it's the most likely thing to probably observe in reality. Yeah.
Okay, thank you.
I think we can ask the next speaker in the meantime to get ready. And I think Roman had a question.
Thank you very much for the presentation.